Hello and welcome. In this video, we will explore key theorems related to polynomials, which are fundamental concepts in the IB Mathematics Analysis and Approaches higher level curriculum. By the end of this session, you will be able to: first, apply the remainder theorem to find the remainder of a polynomial division without performing the division itself. Second, use the factor theorem to identify factors of a polynomial and solve for unknown coefficients. And third, understand and apply the fundamental theorem of algebra, particularly the conjugate root theorem, to find all zeros of a polynomial. Let's begin with the remainder theorem. Our first objective is to apply the remainder theorem. This theorem provides a shortcut for finding the remainder when a polynomial is divided by a linear expression. Let's consider a polynomial, p of x, and divide it by a linear factor, x minus k. The division algorithm states that we can write this as p of x equals q of x times the divisor, x minus k, plus the remainder, r. Here, q of x is the quotient, and r is the remainder. For a linear divisor, the remainder r must be a constant. Now, let's see what happens if we substitute x equals k into this equation. We get p of k equals q of k times k minus k plus r. Since k minus k is 0, the term q of k times 0 becomes 0. This simplifies to p of k equals r. This is the remainder theorem. It states that when a polynomial p of x is divided by x minus k, the remainder is simply p of k. In other words, to find the remainder, you just need to evaluate the polynomial at x equals k. Let's summarize the key idea, p of k equals r. Let's work through an example to see the remainder theorem in action. This will help solidify your understanding. Suppose we want to find the remainder when the polynomial p of x equals x cubed plus 5x squared minus 11x plus 3 is divided by x minus 2. According to the remainder theorem, the remainder is p of k. In this case, our divisor is x minus 2, so k is 2. Therefore, the remainder is p of 2. Now, we just need to substitute x equals 2 into the polynomial. P of 2 equals 2 cubed plus 5 times 2 squared minus 11 times 2 plus 3. Let's calculate this step by step. 2 cubed is 8. 2 squared is 4, so 5 times 4 is 20. 11 times 2 is 22. So we have 8 plus 20 minus 22 plus 3. Adding these values, 8 plus 20 is 28. 28 minus 22 is 6. And 6 plus 3 is 9. So p of 2 equals 9. This means the remainder when p of x is divided by x minus 2 is 9. We found this without performing any long division. This demonstrates the power and efficiency of the remainder theorem. Let's tackle a more complex problem that involves finding unknown coefficients. This is a common type of question in IB exams. Consider the polynomial p of x equals x cubed plus 4x squared plus ax plus b. We are given two conditions. When p of x is divided by x minus 2, the remainder is 20, and when it's divided by x plus 5, the remainder is 6. Our goal is to find the values of the constants a and b. We can translate these two conditions into two equations using the remainder theorem. The first condition, division by x minus 2 with a remainder of 20, means p of 2 equals 20. The second condition, division by x plus 5 with a remainder of 6, means p of negative 5 equals 6. Let's substitute these values into the polynomial to form our equations. For the first condition, we substitute x equals 2 into p of x and set it equal to 20. This gives us 2 cubed plus 4 times 2 squared plus a times 2 plus b equals 20. Simplifying this, we get 8 plus 16 plus 2a plus b equals 20, which simplifies to our first linear equation, 2a plus b equals negative 4. Now for the second condition, we substitute x equals negative 5 into p of x and set it equal to 6. This gives us negative 5 cubed plus 4 times negative 5 squared plus a times negative 5 plus b equals 6. Simplifying this, we get negative 125 plus 100 minus 5a plus b equals 6, which simplifies to our second linear equation, negative 5a plus b equals 31. We now have a system of two linear equations with two variables, a and b. Equation 1 is 2a plus b equals -4. Equation 2 is -5. A plus b equals 31. We can solve this system using elimination. If we subtract equation 2 from equation 1, the 2a-b terms will cancel out. Subtracting the equations gives us 2a minus -5a, which is 7a, and -4 minus 31, which is -35. So 7a equals -35. Dividing by 7, we find that a equals -5. Now we can substitute this value of a back into either equation to find b. Let's use equation 1. 2 times -5 plus b equals -4. This is -10 plus b equals -4. Adding 10 to both sides, we find that b equals 6. So the unknown coefficients are a equals -5 and b equals 6. We have successfully used the remainder theorem to solve for these values. Now let's move on to our second objective, the factor theorem. This theorem is a special case of the remainder theorem and is incredibly useful for finding factors and roots of polynomials. The factor theorem states that for any polynomial p of x, a linear expression x minus k is a factor of p of x if and only if p of k equals 0. Let's break down what this means. The phrase, if and only if, indicates a two-way relationship. First, if x minus k is a factor, it means the remainder when p of x is divided by x minus k is 0. By the remainder theorem, this remainder is p of k, therefore, p of k must be 0. Second, if p of k equals 0, it means the remainder is 0. A 0 remainder implies that x minus k divides p of x perfectly, making it a factor. So, to check if a linear expression is a factor, you simply evaluate the polynomial at the corresponding value of x. If the result is 0, it's a factor. Let's apply the factor theorem to a problem. This example will also show how to fully factorize a polynomial once a factor is found. We are given that x minus 2 is a factor of the polynomial p of x equals x cubed plus kx squared minus 3x plus 6. We need to find the value of k and then fully factorize the polynomial. First, let's use the factor theorem to find k. Since x minus 2 is a factor, we know that p of 2 must be 0. So we set p of 2 equal to 0. Substituting x equals 2 into the polynomial, we get 2 cubed plus k times 2 squared minus 3 times 2 plus 6 equals 0. Simplifying this, we have 8 plus 4k minus 6 plus 6 equals 0. The negative 6 and positive 6 cancel out, leaving us with 8 plus 4k equals 0. Solving for k, we subtract 8 from both sides to get 4k equals -8, and then divide by 4 to find that k equals -2. Now that we have k, we know the polynomial is p of x equals x cubed minus 2x squared minus 3x plus 6. We also know that x minus 2 is a factor. To find the other factors, we can divide p of x by x minus 2. We can use either long division or synthetic division. Let's use synthetic division as it's often faster. We set up the synthetic division with the root, 2, and the coefficients of the polynomial, 1, -2, -3, and 6. We bring down the first coefficient, 1. Then we multiply 2 by 1 to get 2, and add it to the next coefficient, -2, to get 0. We multiply 2 by 0 to get 0, and add it to -3 to get -3. Finally, we multiply 2 by -3 to get -6, and add it to 6 to get 0. The last number, 0, is the remainder, which confirms that x minus 2 is indeed a factor. The other numbers, 1, 0, and -3, are the coefficients of the quotient. Since we started with a cubic polynomial and divided by a linear factor, the quotient is a quadratic, x squared minus 3, so we can write p of x as the product of the divisor, and the quotient, x minus 2 times x squared minus 3. To fully factorize, we need to factor the quadratic term x squared minus 3. This is a difference of squares. X squared minus 3 can be written as x squared minus the square root of 3 squared, which factors into x minus the square root of 3 times x plus the square root of 3. Therefore, the fully factorized form of p of x is x minus 2 times x minus the square root of 3 times x plus the square root of 3. Let's look at another example of the factor theorem, this time involving a polynomial with a higher degree. We are given that x plus 3 is a factor of the polynomial p of x equals 2x cubed plus 9x squared plus ax plus b. We are also told that when p of x is divided by x plus 4, the remainder is negative 18. We need to find the values of a and b. We can set up a system of two equations using the given information. The first condition, that x plus 3 is a factor, means p of negative 3 equals 0. The second condition, that the remainder is negative 18 when divided by x plus 4, means p of negative 4 equals negative 18. Let's substitute these values into the polynomial. For the first condition, we substitute x equals negative 3 into p of x and set it to 0. This gives us 2 times negative 3 cubed plus 9 times negative 3 squared plus a times negative 3 plus b equals 0. Simplifying, we get 2 times negative 27, which is negative 54, plus 9 times 9, which is 81, minus 3a plus b equals 0. This simplifies to our first equation, negative 3, a plus b equals negative 27. For the second condition, we substitute x equals negative 4 into p of x and set it to negative 18. This gives us 2 times negative 4 cubed plus 9 times negative 4 squared plus a times negative 4 plus b equals negative 18. Simplifying, we get 2 times negative 64, which is negative 128, plus 9 times 16, which is 144, minus 4a plus b equals negative 18. This simplifies to our second equation, negative 4, a plus b equals negative 34. Now we solve the system of equations. Equation 1 is negative 3, a plus b equals negative 27. Equation 2 is negative 4, a plus b equals negative 34. Again, we can use elimination. Subtracting equation 2 from equation 1 will eliminate b. Negative 3a minus negative 4a is a. Negative 27 minus negative 34 is 7, so a equals 7. Substitute a equals 7 into equation 1. Negative 3 times 7 plus b equals negative 27. This is negative 21 plus b equals negative 27. Adding 21 to both sides, we find that b equals negative 6. So the values are a equals 7 and b equals negative 6. This problem demonstrates how to combine the remainder and factor theorems to solve for multiple unknowns. We now arrive at our third objective, understanding and applying the fundamental theorem of algebra and the conjugate root theorem. The fundamental theorem of algebra is a cornerstone of polynomial theory. It states that if p of x is a polynomial of degree n, then p of x has exactly n zeros in the complex number system. This means that a cubic polynomial has 3 zeros, a quartic has 4, and so on. These zeros can be real or complex, and they can be repeated. A crucial consequence of this theorem for polynomials with real coefficients is the conjugate root theorem. The conjugate root theorem states that if a polynomial p of x has real coefficients, and if a complex number p plus qi is a zero, then its complex conjugate, p minus qi, must also be a zero. This means complex zeros always come in conjugate pairs. You will never find a polynomial with real coefficients that has a single complex zero without its conjugate. This theorem is incredibly powerful because if you find one complex zero, you automatically know another one, which can significantly simplify the process of finding all zeros. Let's apply the conjugate root theorem to a problem. This example involves a cubic polynomial with an unknown coefficient. Suppose negative 3 plus I is a zero of the polynomial p of x equals ax cubed plus 9x squared plus ax minus 30, where a is a real number. We need to find the value of a and then find all the zeros of the cubic. First, since the coefficients of p of x are real and negative 3 plus I is a zero, the conjugate root theorem tells us that its conjugate must also be a zero. The conjugate of negative 3 plus I is negative 3 minus I. So we know two of the three zeros of this cubic polynomial. These two zeros correspond to a quadratic factor of the polynomial. We can find this factor by multiplying the two linear factors. The factors are x minus the first zero and x minus the second zero. Multiplying these together, we get x squared plus 6x plus 10. This is a real quadratic factor of p of x. Now we know that p of x can be written as the product of this quadratic factor and a linear factor. Since p of x is a cubic, the linear factor must be of the form ax plus c. So p of x equals x squared plus 6x plus 10 times ax plus c. We can find the values of a and c by comparing the coefficients of this expanded form with the original polynomial. The coefficient of x cubed in the original polynomial is a. In our factored form, it's the product of x squared and ax, which is ax cubed. So the coefficients match. Let's look at the constant term. In the original polynomial, it's negative 30. In our factored form, it's the product of 10 and c, which is 10c. So 10c must equal negative 30, which means c equals negative 3. Now we have the linear factor, ax minus 3. Let's use another coefficient to find a pa. Let's equate the coefficients of x squared. In the original polynomial, it's 9. In our factored form, it's 6a plus circa. So 6a plus c equals 9. We already found that c equals negative 3. Substituting this in, we get 6a minus 3 equals 9. Adding 3 to both sides gives 6a equals 12, so a equals 2. We have found the value of a. Now we can find the third zero from the linear factor. The linear factor is ax plus c, which is 2x minus 3. Setting this to 0, we get 2x equals 3, so x equals 3 over 2. Therefore, the value of a is 2, and the three zeros of the polynomial are negative 3 plus I, negative 3 minus I, and 3 over 2. Let's work through one more example involving complex zeros, this time with a purely imaginary zero. We are given that one zero of the polynomial p of x equals ax cubed plus the quantity a plus 1 times x squared plus 10x plus 15 is purely imaginary. We need to find the value of a and all the zeros. A purely imaginary number is a complex number of the form bi, where b is a real number and b is not 0. Let's call this 0 bi. Since the coefficients of p of x are real, the conjugate root theorem tells us that its conjugate, negative bi, must also be a 0. These two zeros, bi and negative bi, correspond to a quadratic factor. Multiplying the factors x minus bi and x plus bi, we get x squared minus b squared I squared. Since I squared is negative 1, this simplifies to x squared plus b squared. This is a real quadratic factor of p of x. Now we can write p of x as the product of this quadratic factor and a linear factor, ax plus c. p of x equals x squared plus b squared times ax plus c. Let's expand this and equate coefficients with the original polynomial. Expanding gives ax cubed plus cx squared plus ab squared x plus cb squared. Comparing this to ax cubed plus the quantity a plus 1 times x squared plus 10x plus 15. Let's equate the coefficients of x squared and x. Equating x squared coefficients gives c equals a plus 1. Equating x coefficients gives ab squared equals 10. We also know the constant term is 15. From our factored form, the constant term is cb squared. So c, b squared equals 15. This is our third equation. We have a system of three equations with three variables, a, b, and circa. Let's solve it. From equation 2, we know ab squared equals 10. We can substitute this into equation 3. This gives us c times 10 equals 15, so c equals 1.5. Now that we have c, we can find a using equation 1. 1.5 equals a plus 1. Subtracting 1 from both sides, we find that a equals 0.5. Finally, we can find b squared using equation 2. 0.5 times b squared equals 10. Dividing by 0.5, we get b squared equals 20. So b equals plus or minus the square root of 20, which simplifies to plus or minus 2 times the square root of 5. We have found a and b. The purely imaginary zeros are plus or minus 2i times the square root of 5. The third zero comes from the linear factor ax plus c. The linear factor is 0.5x plus 1.5. Setting this to 0, we get 0.5x equals negative 1.5, so x equals negative 3. So the value of a is 0.5, and the three zeros are 2i times the square root of 5, negative 2i times the square root of 5, and negative 3. Let's recap what we've covered. We started with the remainder theorem, which allows us to find the remainder of a polynomial division by evaluating the polynomial at a specific point. We saw that p of k equals r, where r is the remainder when p of x is divided by x minus k. Then we explored the factor theorem, a special case of the remainder theorem, which provides a simple test for factors. We learned that x minus k is a factor if and only if p of k equals 0. Finally, we delved into the fundamental theorem of algebra and the conjugate root theorem, which are essential for working with complex zeros. We established that complex zeros of polynomials with real coefficients always come in conjugate pairs. These theorems are powerful tools for analyzing polynomials, finding their roots, and solving for unknown coefficients. Mastering them is crucial for success in IB mathematics AAHL. To help you practice and master these concepts, here are 5 IB-style practice questions. Pause the video, work through them, and then resume to see the fully worked solutions. Question 1. Find the remainder when 2x cubed minus 5x squared plus 8 is divided by 2x minus 1. Question 2. The polynomial p of x equals x cubed plus ax squared plus b x plus 4 has factors x plus 1 and x minus 2. Find the values of a and b. Question 3. When the polynomial p of x is divided by x squared minus 3x plus 7, the quotient is x squared plus x minus 1, and the remainder is r of x equals ax plus b. Given that p of 2 equals 29, and p of negative 1 equals negative 16, find the remainder r of x. Question 4. Show that x minus 2 is a factor of p of z equals z cubed plus mz squared plus the quantity 3 meters minus 2 times z minus 10 meters minus 4 for all values of m. For what value of m is x minus 2 squared, a factor of p of z? Question 5. A real polynomial p of x equals x to the power of 4 plus ax cubed plus bx squared plus cx minus 10 has two integer zeros, p and q, and a complex 0, 1 plus chi, where k is a non-zero integer. Given that p plus q equals negative 1, find all zeros of p of x. Let's start by writing a simple equation on the board. Here is the equation x squared plus y squared equals 1. Now let's highlight the x squared term. And now, let's highlight the y squared term. This equation represents a circle with radius 1 centered at the origin. Thank you for watching. That concludes our session on polynomial theorems. We've covered the remainder theorem, the factor theorem, and the conjugate root theorem, along with several worked examples and practice problems. Remember, these concepts are interconnected and form the foundation for solving more advanced polynomial problems. Keep practicing, and you'll build confidence and mastery. Thank you for watching.